I think now we are ready. Dr. Emre Uğur is the associate professor in the computer engineering department of Boğaziçi University. Since I saw this small introductory title, I'm going to leave it up to him to describe the rest quickly, not double take. Thank you for giving us this talk. I'm sure it will be very enjoyable and informative.
So we have like 40 minutes. How long do we have for the talk?
40, 45, up to you.
Okay.
Not too strict.
Okay. Thanks a lot, Barış Hoca and all for inviting me here. So actually, I've been in this seminar as an audience before, so I think it's my first time to present. Thanks a lot. So Barış already introduced me. So I am in the computer engineering department in Boğaziçi University, and I am the chair of Cognitive Science Master Program, which is an interdisciplinary program in our university, and I lead a lab named Colors. So I have my PhD from METU, and I worked as a research scientist in Japan for 4 years, then in Innsbruck for 3 years. And from time to time I visit, I'm still visiting, but I visit Osaka University in different positions. Okay. So these are general slides. I think I will skip this. Everybody knows about Boğaziçi University. I mean, because we live in Turkey now, we are quite close by. But maybe you don't know about our planned research center, which is named ROYA, Robotics and Artificial Intelligence Laboratories, Robotic ve Yapay Akıl Laboratuvarları. This was a infrastructure research center project that was accepted to be supported by presidents of something. That time, now the name changed, Strateji Daire Başkanlığı, and I don't know what to say, an interdisciplinary project with members from very different departments, like maybe KUIS AI in Koç University, but it was led by 4 faculty members who do robotics. And it was a quite generous support because it was related to infrastructure. We were going to build a research center that's centered on robotics. And actually, we were going to even enlarge the campus of the university. So for people who know KUIS AI campus, so this building is just next to KUIS AI campus, and we were going to buy it with our budget, and then it was quite fine for robotic infrastructure. We were going to build up the labs, move our labs there, and then do joint work. But then something happened 2 years ago, almost exactly 2 years ago. So you know, some rector that we had no idea was appointed by the president, and then chaos actually started in the university. I'm not going to talk about this. So I show these slides in all my talks, and probably you are aware of what's going on. Actually, so yeah. So why I put these slides is I know that many other from other faculties in Koç University as well, and students and researchers support us in different ways, and I would like to thank to you all for your support. So it is interesting. I don't know how in your university, but 2 years ago, before 2 years, I had no idea how much academic independence is important, because we were living in this bubble. and everything was fine. Not everything was fine, of course, but in the bubble, everything was okay. But then after things start happening, then we understood how important not only academic, but administrative and financially independence in the university. Okay. So this is a very recent picture that we took. Okay, let's go back to research. Actually, two of my students, Tuluhan and Yunus, they gave a talk in KUIS AI meetings. And now the picture changed. There's a new picture as well. So the name of my lab is Colors. I formed it 6-7 years ago when I first came to Boğaziçi University. So it is what we do is we do stuff related to cognition, robotics, and learning. So now I changed the names, but we have research in basically 3 different tracks. One is related to computational modeling / cognitive science. The other is related to cognitive robotics, cognitive developmental robotics. Today, I'm going to talk on research in this track. And the last one is more related to manipulation learning. So I will briefly mention what we do in, for example, cognitive science track. So we try to understand, using computational tools, we try to understand different cognitive capacities related to embodied perception, affordances, tool use, body representation, time perception in humans. So let me give an example. For example, now we have also a VR lab, but these experiments were done before the VR lab. What we do is, in order to understand embodied perception and affordances, so inside virtual reality, we change the embodiment. How can you change the embodiment? In real life, it is very difficult to change the embodiment. Ali, can you mute yourself? In virtual reality, what we can do is we can change. We can replace hand, for example, with something else, or we can enlarge our body or shrink our body, stuff like that. So because we don't have much time, I'm just going to show you some videos how we change. For example, instead of a hand, so there are different conditions. There are conditions with hands, 5-finger hand, and then there are conditions with without a hand, like a capsule. So when we have capsule instead of a hand, then we lose some capabilities, like we cannot pick and place anymore. And when we cannot pick and place, our embodiment changes, then our perception related to that embodiment changes as well. So in this paper, we showed that adaptation to such embodiments and then change in perception is quite fast in humans. And yeah, change affordances. So this is another example. There is a big literature on time perception in humans. We can segment ongoing stream into events, humans, in a consistent way. So here in this work, what we did was we formed a computational model using neural networks that is able to segment ongoing events. Here you can see that are shown with point light displays. Ongoing events into fine-grained or coarse-grained events, and then we did experiments with humans, and we compared the event segmentation of humans with our computational model. Okay. So from manipulation learning track, of course, I'm not going to give any more details, but what we have is we have manipulation robots here. And then learning generally takes place in simulators. So there's always some sensors outside, some cameras or depth sensors. Sorry, I don't know why it's not showing, but it's not that important. And through self-supervision or through reinforcement learning, the robot acquires different types of skills like grasping, pick place, pouring, tool use, and stuff like that. Yeah, sorry, I don't know why. And some of this work was already presented in one of KUIS AI meetings before. Because it does not load, I cannot skip as well. Okay, good. Okay, today's title was DeepSym and almost end-to-end symbol extraction and rule learning system for long horizon robotic planning. Quite long title, I know, but it includes many things that I would like to say actually. And this work is done in the last track, cognitive robotics track. Okay, so let us motivate ourselves and then think about, so now we start talking about cognition, right? Cognition, long horizon planning. And of course, when we start talking about anything in AI, then in these days, we have a look to the most powerful AI systems, which are large language model based systems. So this is ChatGPT, and then I would like to ask a question. I would like ChatGPT to make planning or reasoning in kind of it is not robotic task, but it is very simple robotic task, let's say. So the question is, make a stacking plan with 3 objects colored with red, blue, and green, such that at the end, blue object stays in the middle. So if I ask you such a question, then the plan would be something like this, right? So there are 2 different plans. So this is one of them. Okay, what do you think? Do you think ChatGPT is able to make such plan? Okay, let me continue. I asked this question today before coming here, but previously I was asking another question, which is very much related. The question was not planning, but reasoning. So they are very, so reasoning and planning are trying to solve the same problem from different directions. So the question that I was asking was, I place a blue object on top of a red object, like here, and a green object on top of the blue object. Which object is in the middle? And both GPT-3 and ChatGPT failed. And I was like, oh, this is great. And I was showing this all the time in my AI classes or related classes, talks and stuff. Until one day, of course, and I was always showing this online. So opening the ChatGPT console and typing this question. And one day, ChatGPT said the blue object is in the middle. Then we noticed that there was an update in ChatGPT in November sometime. So it looks like so it was not that good in such a simple reasoning task. And now it is much better. It can solve this task, right? So it improved. Okay. And today, before coming here, I asked, sorry, yes.
Just a quick question, like, so ChatGPT, does it also store the questions in some database? I mean, like this update is in the software, I assume, right?
Yes.
But does it also store the questions and then somehow works on it and things like that, or not? I don't know. I'm asking.
I think we don't know, but I think we can assume that all the systems are using us as the data generators.
Okay.
So
yeah,
we can give feedback to their answers. So which means that they are probably using our data as well. Then before coming here again in the morning, I asked this question, make a stacking plan with 3 objects, blah, blah, blah. And So it was able to make that plan as well. Place the red object on the bottom, place the blue object on the top red object. So perfect, but still very simple, right? Let's continue. So let's do a bit more embodied. So I'm going slow, but I think it's fine. So the question was as follows. In which sequence, again, it was from today. So I needed to connect early today because ChatGPT servers are down most of the time these days. In which sequence do I need to stack a big cup, a small box, and a large ball in order to create a tall stack composed of 3 objects? Big cup, small box, large ball, okay? And the first part of the answer was, the order in which you stack the objects will depend on the specific dimensions and shapes of the cup, box, and ball. However, in general, it is best to start with the largest and most stable at the bottom and stack smaller and less, which makes complex sense, right? And then this is the way how ChatGPT generally answers the question. So it starts from general answers which summarize the process and then provides the concrete answer later. But then the rest. So in this case, the order would be large ball, big cup, small box, which is not a very stable tower. It says this will create a tall stack composed of 3 objects that is stable and less likely to. So if I ask this question, then probably you are going to give this kind of answer, because you can stack a cup on a flat object and then a ball on the cup such that the ball is inserted inside the cup, because both ball and cup they are large. Which means that, so these large language models, although we don't know exact mechanisms, we know general how they work, but we don't know the details. But they are able to make some reasoning. But this reasoning does not necessarily need to be grounded. So it looks like there's some problem with grounding, even in this very simple case. This object, ball, would not be any stack with a ball on the bottom would not be stable. So this is very common sense knowledge, but this system which worked great, that was not able to make such kind of reasoning. Okay, so there are so many papers now which work on different aspects of these large language models, and chain of thought prompting might elicit reasoning in large language models. So if you change the question a little bit, or if you cleverly ask the question, if you make sure that it is going to give chain of thought prompting, so it might start making better reasoning capabilities. But when we have a look to well-known planning benchmarks, we will see that large language models still can't plan. So let me show you. So this is from the paper in the middle, and actually the OpenGPT was not around while this paper was published, but here you can see that GPT-3 achieves like 0.6%, 0.2%, 6%, 0.0% in this kind of reasoning problems, which means that yes, it looks like they can plan, or they can provide you reasonable answers, but these plans there is no certainty that these plans would be valid plans, and they fail miserably in many planning tasks. Okay, but AI planners do accurate plans since 1970s, right? Since time of Shaky. Shaky was the robot in Stanford, and it is considered to be the first autonomous intelligent robot. But by the way, I see some notifications in the chat screen. What should I do? Should I check them out, or
Up to you, Emre Hocam, if it doesn't affect your flow. Go ahead. If so, we can leave it to the end.
Maybe let's leave it to the end then,
Okay.
because maybe we already passed some of them. So AI planners now, they are a bit more complicated, but the basics were very basic. So what they do is they are given some symbolic description of the environment, like map, rooms, which rooms are connected to each other, with the objects, the object locations in the rooms and stuff like that. In symbolic model. Then the robot has some actions, and actions have preconditions and effects, and they are all in symbolic domain as well. İçerisi dolu. And then, so the given a goal, again, in symbolic description, the robot is able to make plan sequence of actions, plan sequence of actions to achieve the goal. Okay. And now, of course, previously, more basic plans were being used, and now probabilistic planners are used, but still, so if you are interested in, please have a look to this kind of recent article, Shaky from Conception to History in AI Magazine, then you will have some more idea if you have no idea. Okay, so if we have a world model, grounded world model, then we have the tools to make accurate plans. But the problem is how to connect our own world, the robot's world, that is perceivable from its sensors and actable through its motors or other actuators to these symbols. So that was the biggest problem, which is called symbol grounding. So there are symbols that we kind of know can be used for planning. And we have our robot, which with continuous stream of sensor measurements and continuous control. So on one hand, there are symbols. On the other hand, there is continuous measurements and control. How can they be connected to each other? Symbol grounding problem. So, for example, of course, this is not camera view of the Shaky. Camera is on Shaky, but so given the camera view, the robot should be able to map the symbols on the right to the images on the left, maybe. And people most of the time used classifiers. So they first created the symbols, all the symbols possible. Then they detected, so they annotated or did something with the continuous stream of the robot, and then they trained classifiers such that after training classifiers, the robot can now ground the symbols and then make the plans. But so this approach, which were being tried since 50 years now, it looks like 50 years, did not work. Now, we still don't have the robots that can perform in any unstructured environment with high level intelligence. Why it did not work? Of course, people would have different answers to this question. My answer would be, so not only grounding the existing symbols is difficult, but also designing the required set of symbols is also not possible. Can we predefine all possible symbols? I'm not sure. So if I ask you how many symbols should we design for a robot, then probably the answer is infinite. Because so we can create a new symbol, a novel symbol using existing symbols, right? Then, which means that we can generate infinite number of symbols. And so up to now, it was not possible to define all symbols. Okay. And even if we define some symbols and then make the grounding, then still this will be very rigid. So it would break quickly in slightly different environments where either grounding is different or maybe we need some different symbols. So predefining symbols is not, so AI planners are great. They use symbols, but predefining symbols and grounding them did not work up to now. So what we argue is, so the robots, like humans, should discover symbols themselves. And of course, they need to discover useful symbols for reasoning, planning, communication, and language. And instead of symbol grounding, we name this process symbol emergence. So given now, remember our object stacking task. So we will be always doing stacking, by the way. So the robot has no idea about the objects, their properties, how they would behave when the robot interacts with those objects, and how the objects interact with each other. In this case, these are simple boxes. Of course, the objects are very different, like there might be balls or cups or glasses or stuff like that, or containers. And we would like at the end, after learning, the robot to be able to make plans using discovered symbols from its interaction. So that is our goal. And here I am going to first present Alper's work. Alper is my PhD student here. Let's call senior PhD student. Okay, now this is published in Journal of Artificial Intelligence Research. So this process is as follows. Now we start talking about more detailed computational stuff. So the robot interacts with the objects, and the robot has camera. And in this case, the camera can detect objects and get a depth image of the object. Okay. So the robot has different actions, and it interacts with the objects, and it observes the environment using its camera. And from this interaction experience, what it does is, using some neural networks with binary activations, so that is the central point of this work, with binary activations, it learns object symbols, which means that given the image of the object, it is able to generate a symbolic description. In this case, it is binary encoding. And with this binary encoding, it is able to generate binary / symbolic effect description as well. And all the continuous experience of the robot is now converted to binary or discrete experience. And with this binary or discrete experience, now we can train decision trees given object symbols, which is with objects where objects are represented as with binary representations. Using decision trees work on this bit encoding. It is able to predict the effect symbol. And any decision tree, sorry, so I'm getting WhatsApp. Anyways, any decision tree can be converted to the PDDL, problem domain definition language operator, which I showed you in the beginning. So which was used by Shaky Robot like 50 years ago, where, so it's not exactly the same language, but so it is very similar. Each action has preconditions, symbolic preconditions, and symbolic effects. And then in this case, this is probabilistic, where so each action with the same preconditions might generate different effects with different probabilities. And as soon as we have these rules, now we can use conventional AI planners to make plans.
Emre, how often do you do that? Like, because you are using UR5 and the control loop of the UR5 is running at 125 Hertz. When you say this binary action, like how often do you do that? Like you detect the contact and take the binary action, or do you do it in every time step of the control loop?
An action corresponds, I'm going to show an action. So we have 4 actions. 3 of them are push action. And an action means that bringing the robot and effector to the object and pushing it. So the complete trajectory of the robot action corresponds to one action.
So you detect the contact and then take the action, like, because the loop is running, right? The background, robot is moving, and like at some point it's making a contact with the object, and then you take the action.
So let me show you the action and then describe it over it. So first of all, we use simulator all the time for learning. And then each action corresponds to first detecting the object location. In this case, I think object is placed always the same location. So we need to ask to Alper. But so from the camera, the robot detects the object location. And then here, as you can see, and the action starts. We use inverse kinematics in order to create a trajectory to push the object in one of the 3 directions. And after that, when the object is stationary, that interaction finishes. So interaction starts. We take the snapshot of the object. Then the robot pushes the object. Interaction ends. We take another snapshot. Then another action starts. So it is not a closed loop feedback action controller. It is just open loop. We just get the object position, calculate the trajectory, and then execute the corresponding trajectory, and that corresponds to one push action.
I mean, so you assume there is a force sensor at the end effector, is that?
Yes, we assume there is a force sensor as well. Actually, like we have a force sensor in the lab. That's why we also put a force sensor here.
Okay.
Okay. And so we collect data like this. The data we collect is the snapshot of the environment, these pixels before the interaction, the snapshot of the environment after interaction. And then we have another action, which we call stack. Stack action is pick up one object and then release it on top of the other one. And we again take snapshots of the objects before interaction, as you see on the left, and after interaction, as you see on the right. And here you can see that all the information that we have is in high dimensions. So there is no symbols here. There is just pixel values. Then what we do is, again, this is the core. We train neural networks. So encoder, decoder, but these are not autoencoders, encoder, decoder neural networks, which predicts the change of the object position in pixel space, given the image of the object. Okay. So given the image, if this was a box, the object position change would be different compared to a sphere. So this object image is taken, it is encoded in a representation, Then this representation, binary activation units are used to encode this representation in binary. Then we give action information. Then we force the network to predict the effects, which means that if it is an object image with a sphere, and if the action is push left, then the change in the position should be large towards left. And the system needs to encode this image in binary units to be able to make such predictions. So I am going to speed up a little bit. If you have questions, then we can come back to the details. Okay. So I will start talking less about, again, the technical details. But so our system in the end discovered 4 symbols. So because it is represented with binary units, 0 and 1s, you can see the symbolic representations of different objects here. So each row corresponds to one symbol, which means that the images on the upper row create 0, 0 activation in that binary bottleneck unit. Or these objects create 0, 1 activation, or these objects create 1, 0, and these objects create 1, 1. So what we notice here is both boxes with flat surface and cylinders that are placed upright with, again, flat surfaces correspond to the same symbol because they respond the same way to push actions. So from robots' embodied perspective, with push action, boxes and upright cylinders with flat surfaces have exactly the same meaning, which makes sense because so maybe you would call one of them symbol, one of them box, but for robots interactions, if they have the same meaning, then they should have the same meaning symbolically as well. And it looks like one of them objects is rollable, unstable, this is stable, flat surface, and insertable, if we name them. Okay, let me continue because it's already 36 minutes. Then we create a symbolic representation for stack action as well. Okay, at the end, so what we do is we learn decision trees from them. Pardon. And after learning decision trees, the system automatically generated these PDDL descriptions that can be used by AI planners. So here we did not touch anything. We have a workflow, and from robots interactions to this description on the right, everything was automatic, which means that the robot was able to create symbols that can be used for planning. And now we can ask the robot to make some plans. So here we ask the robot to make a plan with these 4 objects. The objective is to create a tower, a low tower whose height is 1. And the plan the robot made was something like this, because it learned about insertability affordance or symbol of the object, and then it learned the symbolic effects. What happens when 2 objects are inserted or stacked on top of each other, depending on their size, all symbolically. And when we change the objective, create a tall tower, now the plan is different. As you see, the robot the planner made a plan such that a tall tower was created. And now we use a sphere, and we would like to create a tower with height 5 with 5 objects. The symbolic plan was something like this.
Where do you make the simulations, Emre? Like, what's the?
In this case, the simulation. Alper, are you there? Alper was planning to come.
Copy.
Ah, yes.
Yeah.
Copelius,
Okay.
Thank you.
previously known as VREP.
Yes, but now we changed it. I mean, now we are using something else I'm going to show. And if you have questions about simulations, Alper can answer. So these are different plans that are made by the robots. And these are different plans. And this work was done during pandemic. We were not using the lab. So we just recently started using the actual robots again. So we needed to publish this simulation only, therefore not in a robotics journal, but in AI journal. So what are the problems? I will be finished in 5 minutes. We did a lot of stuff, yes, but we use predefined actions. So but the capabilities of the robot depend on the actions. And if we have a look to humans or other animals, probably they are discovering the actions themselves. So if we put our robot in an open-ended setting, then the robot should be able to discover its own actions as well. So that is missing here. That is big drawback of this work. Not fully end-to-end yet. We did some feature engineering in effect space. So it was predicting the change not in images, but in pixels. And then, so there are problems probably with scaling up. For example, our system can make plans with one or two objects, but how about cluster of objects, many objects, and their interactions with each other? And the big question is how to integrate top-down influence on symbol discovery, influence of language, existing taxonomies, etc. Actually, we wanted to work this with IQT and ERQT, but we couldn't find a student yet for that. Anyways, so now I'm going to show you some work on progress, the extensions of DeepSym. So what Alper did after this work was in order to represent multi-object symbols, he used some attentive deep effect predictors. So let me show you the new setting. In the new setting, not only two objects, but 3 or more objects exist. So this video is not perfect, but let me show it again. You know, what it needs to learn is if it puts this small box on the left and this other box on the right, and if it grabs the bar, then the other two objects will be lifted up together as well. And then it should be able to make this prediction, again, using some symbols that encode those 3 objects. And for that, again, if you have questions on details, Alper and we can explain later. What he did was, after segmenting the objects and getting the encoding and attaching the action vector, he used multi-headed self-attention such that so the relations of the different objects are automatically propagated to each other. Again, symbolically, and then in this way he can make effect prediction. So this is an example plan again based on that system. Given these initial states, Alper would like to create the robot to create a plan that brings the initial state to this goal state, and the plan is as follows. When we execute it, first this object is placed on top of the other one. Then this bar is moved to the new location. Then this black object is placed to its new location. And finally, this red object is placed on top of this bar. So this example or other examples do not show the full power of this system. We are still working on this self-attention mechanism. Show anyway. Reload. Show anyway. Okay. And Tuba is our master student. Instead of self-attention mechanism, she tried to do the same thing, which means that symbols for varying number of objects that compose composite structures using graph neural networks. So let me show her learning setting. In this case, it is stacking, but now, as you see, it is a bit more complicated. So multiple objects are stacked or inserted on top of each other, and the robot needs to learn about multiple insertabilities and stuff. Like now, we have composite objects on the left, and we would like to create symbols that correspond to these composite objects. And for that, she uses graph neural network. So these are a number of examples. Like here, you see a number of objects and their graph representations. And again, so this is a work in progress. If you have questions, maybe Tuba is here, maybe not. I'm not sure if she is here, but we can try to answer. So in short, so what I'm very much interested in is, as maybe you have seen, not only neural or machine learning, or not only symbolic, but combination of both, which is called neurosymbolic approaches. And then we try to push these neurosymbolic robotics in general in the field or in the community. So we try to organize workshops. In both of them, Alper was the first organizer. It was 2 years ago, it was in RSS, and last year, or this year, in 2022, it was in IROS. So we bring experts from both fields, or experts who work on intersection, and then we discuss how we can make use of both neural and symbolic approaches together. Is it my last slide? So I will finish up. So I'm sorry that I didn't show you any real robot today, but I did some similar stuff when I was in Austria, with not these very advanced methods, but with more hectic methods. But this video shows that what we learn in simulators can be actually transferred to the real robots. So here you are going to see again the plans. So the symbols were learned in simulator, and then they were transferred to the real robots. And then again, when we ask the real robot to make plans with objects, there is a camera. From the camera, the object features are detected, and they are converted to symbols. Then the planner makes a plan, and then this is the plan execution. And that was young me. So there are different types of here, for example, you can see that. So this was some interesting plan, maybe. Now there are a number of different objects, as you can see. Some of them are insertable, some of them are very thin, not very stable, and the robot was able to make this plan, like insert all these pens inside the cup at the end. And of course, so here maybe there was some problem with the execution at the end.
How does this approach take into account the uncertainties in object geometry, like material properties of the objects? I could imagine, these are all rigid objects, I assume, right? Like
yes.
They are not soft objects. And if the geometry, you're looking from top, like with the camera, if the geometry is changing, and that will change naturally the inertia of the object, so. Do you take into account somehow the uncertainties in this approach?
So theoretically, yes, because we are using probabilistic planners. So our actions effects are probabilistic, and then so the plans actually are probabilistic. So we cannot detect these material properties and stuff, but if those uncertainties exist in our experience and data, because those probabilistic actions are learned from data, those uncertainties are there. So theoretically, we take into account. But in practice, of course, we learn in the simulator. And the uncertainties in the simulator are different from uncertainties in the real world. So in practice, when we make transfer, it won't work. So because of this gap in between simulators and the real world. And that's important. So we need the sensors for that. But yes, so that's a very important point.
Thank you.
So this was my last slide. Thank you all for listening. It's been 50 minutes, sorry. But so I hope you enjoyed. Thanks.
Thanks, Emre Hocam, for the talk. If anybody in the audience has a question? If not, I can ask some. Very nice work. Few things. So these are the discrete actions, right? Can we
Discrete actions.
take them, like what would it take us to take it to more parameterized actions, pushing from arbitrary directions, arbitrary locations, and perhaps related to that, yes, I agree that robots need to keep learning symbols, whatever they need. However, with such an approach would be limited with the like the binary layer size, right? If you have D layers to power D objects per action, of course you concatenate them. But even if you concatenate them, like the space representation, will overlap probably. So it can be like move to more realistic continuous actions and perhaps truly potentially infinite number of objects.
Yes, thanks, Barış, for this question. Some slides did not work. I copied. Now I think so. I will be able to show it. Thanks to this question. So this is Alper's new work. So as you said, the shortcoming is not only actions are predefined, but they are not parametric. So now Alper is working in a more richer environment where he uses parameterized actions. Maybe velocity profile or direction of approach or other things. I don't know. The speed and in a richer environment that you can see on the right. So this is AI tutor kitchen environment. And here you can see his initial interactions, not his, but the robot's initial interactions with the environment, where now, in this case, the actions are parameterized. So the action is like, given the object location, the end effector is making a ballistic movement towards it with a lot of noise. And then some grasp probability. And with this, we hope that the robot is going to discover action primitives such that grasp, pick up objects, pull drawers, open up cabinets, push buttons, and stuff like that. But the image in this, not image, space, exploration space, in this case is huge. And it is indeed very difficult to deal with that huge space of exploration. But with this work, we hope that Alper is going to, but this is extremely difficult, simultaneously learning object and action symbols from completely continuous object space and action parameters. Very, very difficult, very challenging. But Alper is very smart. So he's going to solve this, I hope. So this is one part of my question. The second part is, so when we use discrete symbols in making plans, then of course, even if we incorporate uncertainty, still our plans would fail, right? Or there's high probability that our plans would fail. Like as humans, what we do is we do plans probably in multiple levels. First in highest abstraction level, then we also start thinking about the continuous parameters and stuff as well. Like if we would like to load a truck of our car, then we can do, for example, mental simulation of the object placements, which is very continuous process, mental simulation. So, and then I believe that what we need to do in robotics is we also need to do plans in multiple levels, not only in symbolic level, but the plans that are done in symbolic level should be checked out in more continuous levels as well. And so if we check out the literature, it's called B-level planning, so in both levels. But maybe we need to make the plans in more than 2 levels, maybe 3, 4, I don't know. So what I think the key is we need to create abstractions in different levels, which enable us to make reasoning and planning in different levels of abstractions. Which is again beyond now. Yeah, so that is my answer.
I think like maybe that's the only way of doing it, right? Maybe it's not beyond, it's now. Like I think fully solved you need hierarchical planning and really good mix of classical and learning algorithms, right? Because I mean, motion planning is, if it's not too dynamic, you'll more or less solve, right? Why would you need to like again create a symbol for it and learn the action? If it's just grasping, if it's not, of course, balancing a ball, you may want to learn, but grasping something, it's a solved problem. Why are we resolving it? And I think like a more hierarchical approach might have been, I don't know.
Yeah, I agree. I agree.
And one last thing, if you have time, I mean, it can be argued that at least the first work, not the following ones, but could it be argued that it's actually effect clustering rather than object finding?
Yeah, actually, it is not. So is the question, does it correspond to clustering?
No, like it's clustering in the analogous sense, not like fully clustering, but grouping together effects or potential effects of objects or something like that.
Yes. So what we did was we tried to avoid that. Because I don't believe in clustering. So clustering is a unsupervised method, and depending on the metrics and on the method that we use, on the feature space, everything. So whenever we run clustering, we can get a different result, right? So if we do effect clustering with different methods, with different metrics, we can get different clusters. I think we should not go in that direction. I think what we should go in the direction where we need to get useful effect categories, not any effect categories, useful for planning and reasoning. And for that purpose, we didn't do any clustering. So in this case, the effects here, you can see my cursor, I think, on the right. The effects are continuous, but these discrete object categories are forced to predict continuous effects. Of course, the prediction is not perfect, but the loss is calculated by taking the difference between the effect categories that are created from autonomously created object categories and the actual observed continuous effects. And in that sense, there is no clustering, and I think that would work better, much better. Otherwise, we always need to play with hyperparameters of the clustering method to obtain the clusters that we are interested in. I think we should not go in that direction.
Playing devil's advocate, at least for this, you will still get very clear clusters. Just for this story problem. and pushing a
Yes, yes, we can. You are right.
I agree with you generally, like I agree.
Uh-huh.
That's
But you know, so I was doing this. I use clustering, and maybe you also know that, I think. So in my previous work when I was doing my PhD, I used X-means clustering to cluster these effects. But then again, I needed to do a lot of tricks. So we always think we will get clear clusters, but still, it's not always the case.
and that's why I asked. I don't know.
Yeah.
So, go on. Yeah. Any other questions? If not, let's thank the speaker. Thank you for. Oh, sorry. Oh yeah, we have some things in the chat. Sorry. Oh, that's related to ChatGPT.
Oh yeah. And these are all my students.
Emre, I have a quick one more question. Like,
Sure.
if the mapping, like in your example, the mapping between action and effect are relatively simple, right? If that mapping is more complex, would this still be working? I can give you an example, like one of the classical tasks in robotics is this peg in a hole kind of experiment where the action and effect are not that much clear, like compared to what you're doing in here. Like you're pushing forward, so you know what the effect is going to be, kind of thing. But in the case of inserting a peg in a hole, you know, that there are some uncertainties or some mapping between action and effect is not that clear, in my opinion. So would that be able to implement this approach in there? Like, in general, questions, if the action and effect are not that much of clear, would this still work?
Yeah, so this approach assumes simple actions, actually.
Right.
As you see, like in actions, here you can see actions are discrete and very simple. Like object representation is complicated, therefore we need to use an encoder. Effect representation is kind of complicated, we need to use decoder. But for action, we don't do much. So we need to do more in order to work with more complicated actions.
Yeah, I mean, like I can give you even a simple example. Let's say you have a larger box, and if you push it from the corner of that box, the effect will be like translation and rotation. So,
yes.
I mean, it is a bit more complex than like just translation or just rotation. So what would you do in that case, for example?
I think that with some uncertainty, we should be able to predict position and orientation as well, I guess. And so there is nothing against using force sensor predictions in force sensor as well. So this kind of systems, I think theoretically it is possible, and we just need to work with the architecture, the neural network and stuff, and we need to collect a lot of data. But I saw maybe Alper, do you have an answer for this question? I'd like Alper to answer as well.
I believe for those kinds of problems, we need to think that action as a policy. So in the high level, we plan, okay, I'm going to peg the stick on the hole, and the result will be in the high level, the peg will be in the hole. So this system will just predict that part of the change, and there should be another low-level system where there's a like policy network or some sort of simple function that just sticks the peg into the hole. So some sort of bi-level system. Otherwise, I don't think we need to learn symbols for very low-level tiny details of the position of the object, or in the case of pushing the box from the corner,
Because
that's
like,
just
I mean,
some
if,
stochasticity we cannot model. So
yeah, like as soon as the geometry changes, since the inertia of the box is gonna change, the effect is gonna be again different. Like I can make a box, simple box, but I can change the box geometry a little bit, and the effect is gonna change.
yeah, you are right.
Yeah.
Yeah, you are right. I also think about that problem too. So that's really a problem if we think in the pixel space, even if the effect is the same, in our senses, the like pixels, the change in the pixels are different. So I think first, before that, before trying to model that kind of change in pixels, we might model the change in the proprioceptive sensors of the robot, because they are irrespective of the environment, and it's mostly low dimensional. So, for example, we can understand whether the box has gone into some place or another by trying to touch from different directions in the temporal sense. For example, I push the box from the corner, and or like let's go to your example. So there are two objects with different shapes. I push the object from the same direction, and the object goes to the same place. So if I try to touch it after pushing, I will get the same effect in my proprioceptive sensors, even though their shape are different. But this is just pure speculation of me. That's really a problem. I don't know how to efficiently solve it.
Yeah, I mean, like, I guess my point is, or my suggestion is this, I think, like, I feel like this approach is lacking learning the dynamics of the behavior. So maybe that needs to be integrated, like learning the dynamics, that somehow, like some way of like maybe learning that dynamics, it seems to be important to me. Is that kind of making sense?
Yeah, it makes complete sense, I think. So we needed to simplify things like this open loop push or stack actions, and then we didn't think beyond. But for more complex actions, I agree that so we need to integrate that kind of dynamics somehow. Then it is a bit chicken and egg problem, which needs to be solved as well. Yeah, but you are right.
Thank you.
Thank you. Okay.
Questions? You have something in the chat,
I think we don't have anything in chat.
Thank you, Emre Hocam.
Sorry?
Thanks again for your talk.
Okay.
Very nice. And I guess that's it for today. Hope to see you some other time soon.
Okay. Yeah, thanks a lot.
Thank you for the talk.
It was nice to see you, Çağatay Hocam, Barış Hocam. Görüşürüz. Hoşça kalın.